Greetings, everyone, and thank you for joining us today for the second in our webinar series on concrete bridge durability. Today's webinar is Don't Patch It, Repair It, led by Chris Ball, whom I'll introduce here in just a minute. This series is being brought to you by Vector Corrosion and the National Concrete Bridge Council. We teamed up together when Vector came to us and said, hey, we think there's a lot more information we could help you all provide. The National Concrete Bridge Council is a consortium of 10 industry groups, all aimed at promoting concrete bridge quality, both construction and design. And one of the things we put into our strategic plan a couple years ago was about trying to disseminate more information on concrete bridge stewardship, as we like to call it, just the overarching, how do we take care of our concrete bridges? And that was sort of the genesis then for this webinar series. And you can see there on screen the logos of all the industry institutes that are part of the National Concrete Bridge Council. And you can always go to our website, which is nationalconcretebridge.org, or you can always just Google search National Concrete Bridge Council. Again, this is the second in our webinar series, and I'd encourage you to sign up if you haven't already for the remaining 4 sessions. And you see here on screen the titles of the topics we're going to cover. We're going to be getting into a lot more in-depth detail on some of the treatments, from electrochemical to encasements to cathodic protection. So there's a good series of educational opportunities coming throughout the next 6 sessions into March of next year. So when we get to the end, we'll do a moderated Q&A, and this is also a competition. And what I mean by that is the person who asks the most or best questions, not necessarily the most, but the best questions as picked by our presenter, will receive a $100 Amazon gift card. So again, encourage you to stay with us to the end and ask questions. And again, we're looking for those good questions in the eyes of the presenter. So our presenter today is Mr. Chris Ball, who's the Senior Vice President of Sales and Marketing for Vector Corrosion Technologies. He has over 25 years of construction experience in the industry, is a member of a number of industry professional groups you'll see on screen. I'm not going to read them all. All of these are really focusing on concrete repair, and Chris is therefore, through his involvement in this and his experience in the industry, is one of the foremost in the country on concrete repair. And so we're really pleased to have him joining us today. So with that, I'm going to turn it over to you, Chris.
Okay.
And probably shut off my camera as well and listen in. So thank you.
Well, thank you. I appreciate the kind words there, Greg. Some of that probably just comes with time in the industry. But before we get started, I just really wanted to say, thank you to yourself, Greg, and to the NCBC organization and your industry members for their interest in promoting, rehabilitation of structures and extension of service life. It's a very important topic, and it's not only good, financially, but also from a sustainability standpoint. So there's a lot of good messages there. So as we get into the presentation, really the fundamental, I would say, point of this presentation is really just durable concrete repairs. And I've kind of gotten a little bit on my soapbox periodically at times about the term patching, and to me, concrete patching is a common term, but to me it seems very temporary. It's like a patch or a Band-Aid. And we know, from the experience that we have with the various industry organizations, including some of them that are members of NCBC, there's a lot of techniques and technologies that are available to make durable and effective, long-lasting repairs. And so that's really what the primary topic is today. So, just the current state of the repair industry. Corrosion is a big issue, obviously, on structures, and few years ago, NACE or AMP today had directed a study to try to determine what the cost of corrosion is to the economy, and they came up at somewhere around 3% of direct cost of GDP was basically dealing with corrosion, and that there were indirect costs just equal to that, so approximately 6%. But whether it's 3 or 5 or 7, those numbers are significant. I think that's the point, that it's a significant cost. So anything that we can do to keep structures in place is really a good investment of time and time and money. And you see some other estimates that were available on the cost of repair and strengthening customers. We're talking about billions of dollars. And unfortunately, this is a study that was from about 20 years ago. There was a report that about 50% of the repairs were not performing satisfactorily. I would venture to guess that number is probably higher today than then. But the point is that we can always do a better job on just being knowledgeable about techniques and technologies to make durable repairs. So concrete repair, as I mentioned, really heavily influenced by corrosion, and in the U.S., it's significantly driven by the use of de-icing chemicals, which are necessary for keep the roadways safe during the winter time. But it has a residual effect on the concrete. Obviously, you can have corrosion due to marine structures as well, and you can have corrosion that's related to even structures that have no chloride exposure just due to age and exposure to carbon dioxide conditions. But a big driver of what we're talking about is de-icing salt or chloride contaminated structures. So just a few pictures that we've taken through the years of different structures, and some of these, like these two here, this one on the bottom left, is actually a shotcrete repair that was not durable, and I don't think it was necessarily due to the shotcrete itself, but just to look at some of the practices about chipping behind the bars and other things that, at the end of the day, was the actual corrosion issue addressed by the repair. And the same thing here in the top middle. You have to give the owner credit here for applying a protective coating to a structure, and I'm sure it probably helped, but you see the concrete spalling that occurred underneath of the coating. So that treatment in and of itself did not really address the underlying corrosion issue. And then you just other examples of corrosion. Top left is the decks are the visible issues, but in reality, the substructures are the real challenge in a lot of ways, because of the whole bridge is obviously supported by the substructure, and joint maintenance and leaking joints and chloride contamination of piers. And you see on the top left and the bottom right. So basically what's happening is that your corrosion is causing the reinforcing steel to the corrosion products are expanding and cracking the concrete, and it allows more chlorides, and it's just a continual process. And there's a lot of information out there already today that's available. And I was mentioning a few resources that are available to deal with corrosion related repairs. They're available from many industry organizations. Like I said, some of them are members of the NCBC. The International Concrete Repair Institute is very heavily focused on, obviously, concrete repair, and does a really good job. American Concrete Institute, which I'm fairly involved in, has a whole section that's just focused on repair rehabilitation. AMP, obviously, National Association of Corrosion Engineers, merged with the Society of Special Coatings to create AMP, Federal Highway Administration, U.S. Bureau of Reclamation, and there are many of them others out there. But just kind of point out, the FHWA does have a bridge preservation guide, and it's free to download. It was updated in 2018. And I thought it was just interesting. I just pulled a quote out of there, basically in the introduction, that due to limited funds and competition for funds, that bridge owners are challenged to cost effectively preserve and maintain their bridges. But the bridge owners are striving to be more strategic by adopting and implementing systematic processes for bridge preservation as an integral component of asset management. So I think the point we're making, we're going to need to do concrete repairs. Let's do them the best we can and make use of the information that's available today. From ICRI, I'll just kind of show some of the documents I think are really useful, and maybe you just want to jot these down. Or ICRI is icri.org. You have one of the original documents that ICRI created back in the day was the guides for surface preparation for repair of corroding structures. And actually, I'm going to use that as a guide for a lot of my presentation on different types of the process of fundamentally doing good quality repairs. But they also have a nice guide for electrochemical treatments. So these are basically other techniques to help deal with corrosion issues beyond the repair itself. And there's a nice guide from ICRI. I think one of the most popular things you'll see from ICRI are their surface profile chips. And I encourage you to look at those. They're a very good reference. And my understanding, they're also working on some representative coupons for surface preparation and cleaning of reinforcing steel in the repairs as well. But these chips are basically a good reference to give you a guide for the surface profile or surface roughness for anything from sealers and coatings to even concrete overlays. And some manufacturers will actually use the concrete surface profile or CSP number to give the contractors and the owners a guideline for the amount of surface preparation that they're looking for their materials. ICRI also has a concrete surface repair technician certification program. It's fairly comprehensive. There's two parts. The first part is online kind of learning, and then there's actually a practical, like hands-on exam where you do things. It starts off by learning what is concrete repair, and then you end up doing things such as making sure they understand slump testing and direct bond testing through the surface repair technician certification program. Once again, other industry resources that are available. On the ACI side, I think there's some really nice documents out there through the repair application procedures. This is the ACI committee E706 that puts these together. And there's a series of these. They're available for online learning. They're free. They're free available to non-ACI members. You do have to register to download them, but there's ranges from epoxy injection to there's shotcrete repair. There are form and pour, form and pump techniques, and it's really a practical guide for contractors. And I think it wants more education. And also I mentioned the Bureau of Reclamation, the practices for some of the research. These are a little bit more technical guides that's available to things that they're using on the reclamation side. Have some really good uses, obviously on the bridge market as well. So those are, I just wanted to point out from, like I said, from all of our education and resource standpoint, things are available to help all of us improve the repair and rehabilitation of bridges. When Greg did the introduction, he said this is the second in the 6-part series. The first part was focused more on the evaluation side. I just kind of pulled this up. This is a nice, I think, a flow chart that we've put together. It's free also. You can contact us for a copy, or it's available on an educational website called WeSaveStructures.info. So basically the point here is to rather than just jumping in and doing the repair or a patch, as you may say, if we're really going to look at the durability of structures, we need to kind of look at it more holistically and really fundamentally have an understanding: is this crack that you see visually, is it caused by corrosion? Is it caused by structural issues? Is it caused by ASR? All those types of things may lead you down to a different path on how you might want to fix a structure. So having an understanding of the cause of the damage through an evaluation, and determining the not only the cause but the magnitude, and then you develop your repair strategy based on the owner's needs and budgets, and all the way through quality control in the field. And once again, I think it's just a nice little guideline. It's available at WeSaveStructures.info. So we talk about concrete repair. Obviously, if you're on this webinar, you're interested in the subject, and unfortunately, I probably spend too much time driving underneath bridges and looking up at the condition, particularly of concrete's my interest. But what is the purpose of the repair? You see a visual damage. You see this is a photograph of netting that's been placed on this arch bridge, basically trying to contain any type of concrete deterioration or spalling. So we want to replace the concrete spalled and delaminated concrete, and it's going to improve the safety. It's going to improve the appearance of the structures. And if we follow the right, kind of like proven procedures, the repairs itself will be durable and will provide protection to the reinforcing that is actively corroding in the repair area. So you look at concrete repair, I think most people start off by learning about concrete and in the context of new construction. And I think we need to look at concrete repair a little bit differently, where the repair itself is really in a confined condition. So we're going to do everything we can to have a good quality surface preparation, get good bonding. So the material itself is confined. So we start looking at the repair material properties, and things such as a 10,000 psi concrete or concrete mortar may not be the best thing for the structure. You may be having high cement contents or whatever, and you could have any type of cracking, plastic shrinkage, drying shrinkage, cracking of the repair material will limit the repair's durability. So we kind of starting off with repair material selection can be important, because instead of compressive strength, we want materials that are more compatible from a repair standpoint, which may be things such as the shrinkage of the repair material or modulus or thermal expansion capabilities. So just to kind of show that on the different, bond strength is something we normally don't think about in new construction as well. So the repair material considerations can be different than what you consider for new construction. So once again, these are images from the ICRI guideline for the surface preparation. So, just following some kind of like good techniques. If you look at the images here on the left, if you did a sounding or delamination survey, you may end up seeing that your spalled or delaminated areas follow the reinforcing steel and may have a pattern. I'm looking at the second one here, for example. And if you just chipped out the unsound concrete and did the repairs, all of these little reentrant corners are areas where you're going to have cracking. And so just from the geometry of the repair, by making going ahead and chipping out some sound concrete, and making your repairs either more square or rectangular as possible, is going to help with the cracking resistance of the repair. The other thing to look at is the concrete removal and effectively the reinforcing, exposure of the reinforcing. So we want to basically chip around the bars and it fully expose any bars in the repair area that are corroded, so that you can get the repair material to fully encapsulate the bar. And you also want to make sure you have, there's some materials may claim that it can have a little feather edge. They get kind of thin at the edge, but that's just an area where you can have rapid drying of the repair materials and like weak layers. So having saw cut edges around the edge gives you a nice good shoulder for the repair material to bond to. And then once again, cleaning, you need to clean the steel very well. You want to get rid of all the corrosion product off the reinforcing steel. Make sure you remove any residual cement and chlorides from the steel, and pay particular attention to the back of the bars. make sure that you clean those as well. And here you should see an illustration of a blast cleaning where the aggregates or the blast media is reflecting off the back of the repair and reflecting onto the back of the steel. Bulk concrete removal, this is when you're going to be chipping out basically loose concrete, and also, as I mentioned, you're probably going to be chipping into sound concrete just to make sure that you get the right geometry of your repairs. We want to make sure that we don't do too much damage to the concrete, so the weight of the chipping hammer can be important to remove deteriorated concrete without doing too much further damage to the base concrete or the substrate. And we want to make sure, as I mentioned before, to have a good surface profile and look at the clearance around the reinforcing steel. One good kind of rule of thumb is if you can get a gloved hand behind the bars, that's probably going to be sufficient distance clearance for the repair material to completely surround. These are just an indication of the concrete surface profile that is the document that goes along with the chips or the reference surface profile, and you see the different CSPs. And if you start looking into concrete repair materials, you're going to be going into CSP 5 or greater. And this is nice because it will give you what different types of techniques and tools can be used to achieve the desired surface profile. And then you can use the reference chips to compare to what you see in the field and see if you're getting the profile that you desire before the concrete repair is completed. Once again, surface preparation, saw cut edges. There's some good pictures of that being completed with just a hand grinder. One thing we also want to make sure we're doing is cleaning the concrete and removing any types of fragments or weak pieces in the substrate. And this is where you see this image here in the top right, where this is basically a slice into the substrate, which you see different micro cracking, or some people might call this bruising of the concrete down beneath. So if you're going to rely on the repair material to bond very well to the substrate, you need to have the sound substrate. So be able to come back with a final abrasive blasting or higher pressure water blasting, just to remove these loose pieces and make sure that you have a nice sound concrete surface for the repair material. And then most techniques would require a surface saturated but dry surface. So basically you want to have a fairly wet concrete, but not with any puddling on the surface, to prevent a lot of moisture being pulled out from the repair material into the substrate. So then what you do for the reinforcing protection, if you just follow those procedures that we talked about, and you're going to have very clean steel, you're going to be coming back with the high quality concrete or mortar. It's going to be fully encapsulating the bar in that area. It's going to be a chloride-free material, fresh material, highly alkaline. The steel itself is going to be very durable. In fact, if I would posit that should be one of the last places that actually deteriorate in the structure is the repair. The repair should be more durable than the surrounding substrate concrete over time. But there's times when you may want to look at there's different philosophies on reinforcing protection. You still may want to use just provide additional protection to the exposed reinforcing in the area. You can use epoxy kind of coatings, field applied, just to provide additional protection. You may want to actually even look at that if you have areas of low cover, just to give you some additional protection. And we'll talk a little bit about embedded galvanic anodes. This picture on the bottom right is a picture of an embedded galvanic anode that's connected to the reinforcing steel, which is going to provide protection to that bar. And then also you can use the embedded galvanic anodes in conjunction with the reinforcing coating. So and that gives there's some synergy there where you really are going to provide protection to the steel in the repair through the coating, but the anode is providing protection to the surrounding concrete. And we'll talk a little bit more about that in a second. Can't forget safety. We want to make sure that we're following all the appropriate regulations if you're in the States. You're going to be following OSHA standards, and particularly anything that we're doing with concrete repair. There's going to be drilling, chipping, grinding. All these things are producing silica. So there's a lot of silica regulations, respirators, and other types of silica control. So make sure that that you're familiar with those standards and are providing protection to the workers as they're doing the work. Different types of repair materials. We have your trowel applied repair. They're really usually, more for vertical repairs that are maybe smaller or almost, somewhat cosmetic in nature. You get into like larger, more substantial repairs, you may just go with a quality concrete mix. Form and pour repairs, shotcrete repairs, etc. I would say would be more structural in nature. But whatever you do, these are cement-based materials, Portland cement-based mostly, and that we can't forget the importance of curing. Curing is for durability. If we want to keep the repair material durable, we want to keep it crack-free. So curing is to allow the strength development of the material is really critical. And then what do we do if we want to check the repair? This is more along the lines of quality control. You're going to be doing a lot of things that are documentations, like looking for delaminations, taking photographs. You can do the same thing like concrete mix for new construction. You can do material testing of the repair material. But also there are some guidelines you can see listed here from ICRI or ASTM for direct bond testing. So you can either test the substrate just to see what the direct tensile strength of the concrete substrate is, or probably a little bit more commonly, you would core through a repair into the base substrate and glue a disc on and directly pull it off and see where it breaks. If it breaks in the repair material, if it breaks at the bond line, or it breaks in the substrate, and what the force is that pulls that off. And so that's a good in situ quality control method. So like I said before, if you follow the procedures, the repair areas themselves will be very durable, and will address the corrosion of the repair. Now, this is where we start thinking about the repairs being just part of the overall structure. Repair is going to be durable, but you see here on the bottom right, that's a photo that I took many years ago in the Northeast, where you see just generations of repair, and you're chasing the corrosion issue around the structure, and you see new areas that are marked out. And so for more repair, and eventually that deck's going to need to be replaced at this rate. But we know that when we're doing the repairs, we are actually creating a risk that there's of what we call halo effect corrosion, or new corrosion that occurs in the concrete that is still adjacent to the repair. So this is just a graphic. If you think about the repair here, was originally the area that was corroding. We followed all these great procedures. The steel is going to be very passive in that area. Now you still have a high probability you have chloride contaminated concrete surrounding the repair. And now, instead of the corrosion being in the repair, it's going to want to shift to the area adjacent to the repair. And that's this halo effect or patch accelerated corrosion. And eventually you'll see new corrosion cell occur, just from the difference in the potential between the repair and the surrounding concrete. So we start looking at what can we do to provide additional protection. One method is to look at we call type 1 anodes. These are galvanic anodes that are tied directly to the steel. There's also type 2 anodes, which I'll show you some examples of, which can be installed into holes that are drilled in sound concrete. And then there's even a third type of anode that's a kind of a newer system that's a combination of embedded impressed current and galvanic anode. But these definitions really come out of the ACI repair application procedure bulletin for embedded embedded anodes. So the idea here is that we want to use an anode in the repair to really effectively keep the new anode or the new area that's corroding from being shifted to the adjacent concrete. So these galvanic anodes they're sacrificial. They're made of zinc with an activating mortar to keep it active over time, and the zinc sacrifices itself instead of the steel. And so this is a couple pictures of this type of application. This is showing a concrete repair on the bottom of the beam, and the subsequent repair. And it's just important to point out that these discrete embedded anodes are really just designed to make that repair in the surrounding area last longer. If you're going to do the repairs, it's no tool that you can use to make the repair more durable, but they're not really having any substantial impact on other areas of the structure. It's just type 1 just to make the repairs last longer. There's a large project in the UK, as an example, where you had a combination of anodes used at these interfaces around joint repairs and throughout some larger concrete repairs on the deck. You have other places where you might see this interface between new and old concrete, where you have a corrosion risk. And one area is bridge widening, and you see the anodes kind of placed along this interface. And any type of structural modification could be an area where you have a new and old concrete interface. So that's really just another method to help the investment in the repair last longer. Now, I just want to take a few minutes here at the end just to say, okay, what about the rest of the structure? What are some of the things that we can do to address the durability of the structure that are beyond the repair? And if you look at the bridge preservation guide or any of these other industry documents, there's lots of different kind of techniques. And I'm just going to show you a few here, where this is a project where you had a chloride contaminated substructure, and obviously you have corrosion that's occurring, is causing concrete delamination and spalling. And then this bridge is over the rail track. So just working with the railroad, they want to make sure that they don't have to go back and repair the structure anytime soon. So there's an additional investment beyond the repair just to provide some additional corrosion mitigation. So you see in these form and pour repairs, the type 1 anodes that are tied to the exposed steel. Then you see a series of the type 2 anodes that are being placed into the sound concrete to provide more holistic protection to the columns. And just a little more pictures in here. Here's these type 2 anodes that have been grouted in. You see the anode grouted into the cord hole and an interconnecting wire, and these are all connected to the reinforcing steel as a galvanic anode system. So this is one way you can provide protection beyond the repair. This is a project we were involved in, quite a while ago, in the upstate New York, where they had the adjacent box beams, and really the corrosion problem here was just on one side where you had the drainage from the deck contaminating just this outer face of the one beam. And eventually this beam was going to be replaced, but to kind of hold it they in place, they wanted to not only do the repairs, but just use the type 2 anodes just to provide localized protection just to the area that's actively corroding, just to kind of hold it in place until they could replace the one beam on the structure. So this is an example of what you might want to call targeted protection. You're just using anodes where you have a known risk of corrosion and targeting them to that fashion. There's the completed repairs. Another thing just to kind of point out for durable repairs is, there's carbon fiber or FRP strengthening is being pretty commonly and successfully used for strengthening of structures. And the ACI committees are basically you just want to, if you're going to be strengthening a structure, the strengthening system is rely upon the bond of the FRP to the concrete to transfer the load. So if you're going to be strengthening structures, there's an encouragement there to look at if it's actively corroding, and if so, what can you do to address it? Here's an example of a FRP that's been applied into a corroding structure, and you see some failure of the FRP and rust staining. So this is just one example, one kind of technique where you see the some spalling, chloride-induced corrosion related spalling, and these needed to be strengthened. So this is one technique where they chipped a pocket vertically on a couple sections of a column and connected in distributed galvanic anodes into the slot. Those slots were grouted back, and then the strengthening was placed on the outside. So you have a strengthened structure with a galvanic protection system underneath of it. We also talk about when you get into maybe more severely deteriorated structures, looking at galvanic encasements, and this will be the topic of pretty much a whole series in a few months, talking about galvanic encasements. But effectively, the idea here is you're using galvanic anodes and on more severely deteriorated structures, and you're reinforcing it with a new layer of steel, and the galvanic anodes are placed into that overbuilt section, connected back into the existing reinforcing steel to provide corrosion protection, and then you have concrete that's been placed. And this is commonly used even for abutments. Just an example of this slab bridges. We've been involved in a lot of these in Ohio. Some of the original conditions of the slab bridges, the joint is right over the abutment. You know, in some of the early days, they were doing some repairs, and they started using some galvanic and the small type 1 anodes. But this is more of a severely and widespread corrosion issue. So effectively, they looked at using larger distributed anodes in these repairs, and these are 17. This project's I think 18 years now, and performing very well. So basically, the process here would be to remove the deteriorated concrete. You place your galvanic anodes into the overbuilt section, and then here for Ohio DOT, they use epoxy-coated reinforcing steel just to provide some additional reinforcing in the overbuilt section. Form and pour repairs, and then these actually use self-compacting concrete. And this was one of the first projects that was done in Ohio. So you see the monitoring unit that was installed just to monitor the performance of the anodes over time. And if you're interested in that, we have a paper that's been published with a lot of that data. I can share it with you if you're interested. This is the same structure last year. Like I said, I think 17 years on, and you see some efflorescence and leaking, but overall the structure is in excellent kind of structural shape at this point. Another project that just kind of a more recent one, just we can show as well, is the repair and protection of the historic 3rd Avenue Bridge in Minneapolis. This is a major structure over the Mississippi River, historic structure, and it was, if I remember right, 100-year-old bridge, and the scope of work here was a replacement of the deck and maintaining the existing substructure as well as other things, obviously. But that's the main point we're talking about from a corrosion standpoint. So just to give you an idea of the condition of the arches, these are actually Milan steel. So it's effectively the way I think about it, it's a structural steel frame that creates the arch itself, and then it has concrete cast around it. So it doesn't have a conventional ribbed or smooth reinforcing bars. These are structural steel members. And over the time, the exposure to the age, the environment, de-icing, salt, you see the corrosion of the structural steel frame in the ribs, and you see even in some intermediate locations where you have some corrosion. And so these are more than just a patch or just a small repair. These are more substantial repairs, and there's billions of dollars are being invested in the extended service life of this structure. So a lot of thought was put together for how to extend the life of the structure from a corrosion standpoint as well. And you see in the areas where you have basically concrete damage and concrete removal from the corrosion, the frame here was coated. So this is the white here is the existing coating. There was a reinforcing encasement around that. And to protect the underlying steel here, you see the distributed anodes placed along the structural steel frame at the top and the bottom. And then at the edges where you have the existing sound concrete that's going to be adjacent to the new concrete, that's where we also use some type 1 anodes. You see them connected to a drill and tapped self-tapping screw into the structural steel frame, as well as the distributed anodes to the same connection. And so that's a very, like I said, very comprehensive mix of repair, strengthening and application of corrosion protection to the repair. Now, they also looked at what to do for the other areas which were currently sound, but were actively corroding. And how do you do that? You can actually utilize a technique that's called a corrosion potential survey, where you're effectively measuring the risk of corrosion in sound concrete by using a reference cell. Generally, it's copper sulfate reference cell connected to a multimeter, which is connected into the reinforcing steel. So any areas where you do a corrosion potential survey and you're seeing that you have a high probability of active corrosion, but you still have sound concrete, that's an area where you can look at using other types of protection systems that are more proactive. And in this case, the consultant used a custom designed two-stage anode. Let me just go back one slide. And the way this works is it has it's two-stage. So the first stage is a self-powered ICCP system, effectively a battery that runs the first phase and that could be anywhere from a few months to a couple of years, depending on the design of the system. And during that period of time, you have a higher amount of current that's being generated naturally would have been by a galvanic anode. And then the idea is that you would passivate the active corrosion with this higher current in stage 1, and then when that occurs, over time it'll automatically switch from the battery to the galvanic anode, and then in that point the galvanic anode is designed just to provide maintenance current to keep the steel from corrosion from reinitiating. And these types of systems can be designed for 30 years of protection, 20 or 30 years, pretty straightforward. And so due to the amount of steel that's in the service life that they were requiring for this structure, like I said, they used some custom design anodes with extra zinc. And in the areas where you have active corrosion potentials, these were grouted into place, and they have an interconnecting wire that connects them all together. Then they're connected into the embedded steel. And once that's all connected, the system operates naturally. They can be monitored if you want, or they can just be directly connected and operate like I said, naturally over time. And there you see the installation where you see the coring and the grouting, the saw cuts, and finally the reinforcing connections that are connecting it to the steel. So I guess just in summary, we started off, we talked about the idea of, I would propose over time, if we can move from a mentality of patching, just patching concrete and looking at repairs that are durable. Then we look at how you make the repairs last longer through the different types of industry resources that are already available, kind of proven techniques. And then part of that is also looking at, corrosion management, even either at a localized level around the repairs, or being able to identify other areas of the structure to provide corrosion protection more proactively, so that you not only your repairs can last, but you can have a longer service life of the whole structure. So once again, thank you to NCBC for hosting this, and all of their industry organizations. And I want to thank the audience here for investing a little time with us today. And hopefully you learned a few things, and the information will be available. The slides will be available. So any of those industry guidelines that I mentioned before, which I really encourage you guys to, if you're interested in this, become familiar with, those will all be documented in the slide deck that you'll receive later. But with that, I'll say thank you, and I'll turn it back over to Greg.
Well, thanks, Chris. And I will then thank you again for a great presentation, and appreciate you leading the group here today. And I know we have a number of questions here that I think Ben and Jackie are going to walk through. And again, encourage you as attendees to ask questions. We have some time for some Q&A, and to me, that's the real benefit. You have the opportunity to actually ask an expert live some questions. So with that, I'll turn it over to you all to do the Q&A.
Certainly. Thanks, Greg, and thank you, Chris, for this awesome presentation. We have a load of questions. We might not get to, or we're definitely not going to get to all of them through this presentation, but we will get them to Chris after the show, and so he'll have that whole list. And as long as you've registered, you'll be able to get your contact information and reach out to you with some answers. And so where I'm going to start off with is with Willem. He said most, if not all, state DOTs have comprehensive guides and standards for documents regarding bridge repair. Do you know what other organizations are out there trying to help kind of build uniformity and up-to-date technologies that are, I guess, trying to bring these new technologies to light for these DOTs?
Yeah, I think it's a good question. I'd say that we live in a country that, the states are, fairly independent with some oversight, obviously, but I don't think you need to feel like you're alone. There's lots of information. If you want to start looking at just your specifications for repairs, there's you don't have to start from scratch. I think the starting point I would probably look at would be, well, you have some documents that are available, through Federal Highway or what have you, but I think the International Concrete Repair Institute, if you just start off by looking at the guide for surface preparation, it just you join the organization, you have access to the documents. There's lots of good, and these documents have been around for, I don't know, I'm 30 years maybe. Also in ACI, ACI has, I think, some real good documents. They even have documents that are out there that are available for that can be adopted from ACI 562, the building code. Sorry, the repair code that's being put out there for adoption by building officials. I think there's a lot of good information in there that could be adopted. That's ACI 562 by people in the bridge community as well. And part of that is basically, looking at making it more of a process of making mandatory to do some type of evaluation up front, and also to actually specifically identify what service life you want in design, because there's some bridges that you're going to need to repair, just like, for example, the bridge in New York that I kind of showed with the precast box beam. they knew they were going to replace that section within 10 years. So the objective there was different than if you're doing the Third Avenue Bridge, which is a 100-year project seeking a 50-year solution. So that's really important. So and ACI also has concrete repair specifications as well that might be helpful.
Excellent. This one was a bit of a theme, so I'll try to sum up a few of these questions or try to add them all into one here. But what is the typical useful lifespan of like a galvanic system, and how can you know that it's still working?
Okay. So obviously, vector corrosion technologies, we've been doing this for a long time, and we have a pretty good understanding of how the anodes work, how they age, and how long they'll last, and how you design with them. So on the YouTube, we have a YouTube channel that has a whole presentation that hours worth of that covers these points. But I think in summary, the galvanic anodes will typically last between, I would say, 10 and 30 years. If you look at the like, for example, our standard tables for the spacing of the type 1 anodes, they're based around achieving a certain amount of protection at 20 years, but the anodes will last longer than that. But the real answer is that's kind of like the standard default. If you want to have a galvanic anode system that lasts for 30 plus years, you can do that. You just need to identify that's the objective and have the anode design the system to design to last for the desired service life. The other part of the question is, how do you know that the anodes are still working? And all these galvanic, just impressed current systems, any kind of systems, impressed current systems, I'd say, require monitoring because it's an active system. Galvanic systems generally do not require monitoring, but if you do want to understand if the system is still operating over a period of time, you can set it up that way initially. And effectively, what you're doing is you would take a sample, usually like a sample section of the galvanic anodes. I just use as a reference the Ohio DOT abutment project, where we had 17 years on that project. That whole abutment had anodes across it, but one section at the end were all wired to a monitoring box. And that allows us to go in over time and take readings to measure the activity of the anodes and also the level of performance. So you can definitely do that by setting it up that way up front. And yeah, it's a good question.
All right. Do you have recommended references for those who are not familiar with the basic concepts of cathodic protection to educate themselves?
Yeah, I mean, like, you can start off with go back to like ICRI and ACI. There's an ACI 222 is a corrosion committee. And then you have ACI 562 is the repair committee, or 546. And they'll actually have some references to cathodic protection in those documents. You go to ICRI. The ICRI has a very nice overview guide of electrochemical treatments, which include cathodic protection as well as chloride extraction and realkalization, these other types of methods. And that's a really good overview. If you want to take another step up from there, then I would go to AMP, which is the former NACE. And they have a lot of more technical guidelines and specifications for performance of ICCP and galvanic anodes, their electrochemical chloride extraction. That would be another step up, and that's the organization that you can get certification and educated and certified in cathodic protection in the U.S. is through AMP. Okay,
so we got one here. We've been talking about doing repairs, but would you recommend using some of these techniques in new construction as well?
Yeah, you can. I would say historically, we see most of the systems going into rehabilitation. Having said that, there's a quite a few volume of projects that are new construction. I think the situation you have in repairs that I like to think of it as it's the hand you've been dealt with. You have to kind of deal with it at that point. New construction, you have a lot more flexibility in the original design on different types of concrete, different types of reinforcing steel, even looking at increased cover depths and things like that can lead you more durability. Where I've seen most commonly where you use any type of galvanic anodes in new construction is areas where you, as an engineer, know over time it's a vulnerable place. So you just say, for example, on a bridge deck, you may not use galvanic anodes in new construction over the entire bridge deck, but you may use them around joints or maybe in some of the areas where you have drainage. Maybe you might look at areas around beam ends or things like that where you know over time you have a high probability you're going to have collection of de-icing salt or other things, and you can use them economically in a targeted fashion as supplemental protection in that scenario.
Sorry, I'm trying to sit through these comments. They're coming in pretty fast. So, would you want to elaborate more on the effectiveness of attaching anodes, or using both epoxy coatings and attaching anodes in a repair?
Okay, that's a really good question. So we believe, and we've seen some testing that shows that there's synergy there, meaning the galvanic anode, if you're using a type 1 galvanic anode, it's connected to this reinforcing steel in the exposed steel in the repair, you will see current flow from the anode to the areas outside the repair where you want your protection, but you also will see current flowing to the steel within the repair, which is the area that's close to the anode. By using the combination of galvanic anodes and a reinforcing steel coating, you're effectively reducing the amount of surface area steel it's in the repair from receiving current from the anode, and that allows the anode to have more capacity to provide protection to other areas of the structure. It's kind of a philosophy that you see maybe in underground, piping systems where you have coated pipe that's protected by a cathodic protection system, or even just say coated sheet pile that's protected with a cathodic protection system. Those are basically the dual action where the anode is protecting more like holidays in the coating than the entire bare surface itself. So that's the fundamental benefit.
All right, and I think we are at the end of our presentation window here. Thanks, Chris, for answering all those questions. If you have any more questions, please feel free to reach out to him. He's doesn't sleep at all. He just answers and talks about corrosion questions all day. So
that's
he'll be more than happy to answer anything that you send his way.
Thank you.
Rust never sleeps, and neither does Chris Ball. I guess that's it. All right.
That's exactly it. But with that said, thank you very much, Chris.
Thank you.
Yeah, thank you again, Chris, and thank you everybody. And we look forward to next month's webinar. So hope everybody's already signed up.